Should be streaming.
All right, thanks for coming. All right, for looking ridiculous today. Anyway, what I'm going to try to do here is go over some of the stuff you need to know for the column chromatography experiment. So some of the stuff that you need to know is going to be theoretical, okay? And then some of the stuff that you need to know is going to be very practical. So we will go over the separation scheme and we will go over everything like that. It's going to take about half an hour to do this. All right, but I do want to go over both some of the theoretical and some of the practical aspects of this. Also, I want to go over this in a way where if your classmates couldn't be here today, they can watch this online. So that's what this is for. All right. So first thing we want to talk about is functional groups and polarity. So last time when we did a lab, you guys did separation by distillation, okay? And what is the primary thing that causes separation by distillation? What do we care about? Boiling point, okay? And boiling point is determined by intermolecular forces, right? The stronger the intermolecular forces, the higher the boiling point. So polar functional groups are going to have higher boiling point than non-polar functional groups among the same size molecules. Very large molecules will have very strong dispersion forces. So boiling point is one way that we separate things. Can we separate everything based on their boiling point? No. Now, if we could, we would teach you distillation, and then we would say, have a nice life, you know everything there is to know about separation in chemistry, right? But it doesn't work that way. The reason that we have so many methods of separation is because no one method is good for everything. So the method that we want to look at today is column chromatography. And column chromatography is another method that essentially separates by polarity, but it does it in a very, very different way. So what I want to look at here is, just briefly, a couple of different functional groups to remind us of the functional groups, and then talk about their relative polarity. All right, so if we look at this first one here, what is this? It's an alcohol. Are alcohols polar or non-polar? Polar. And in fact, that's exactly what you separated last time by their boiling point, right? You used a 4-chain alcohol and a 4-carbon alcohol and a 2-carbon alcohol, and you were able to separate them. And we could separate them based on their boiling point. How about this next one? What do we call it if there is no heteroatom, no functional group? What's the simplest organic functional group? Alkane. So this is an alkane. All right. Are alkanes polar or non-polar? Relatively non-polar. Okay. Good. How about the next one? What functional group is this? That's a ketone. Is a ketone polar or non-polar? Polar. How about compared to an alcohol of the same size? Which is more polar, the alcohol or the ketone? The ketone is less polar than the alcohol. So if I ask which is more polar, the answer would be the alcohol. Why is an alcohol more polar, if you will, than a ketone? Because it has hydrogen bonding. The alcohol has the OH, and the OH is capable of hydrogen bonding. So the reason we're going over this is you're hopefully starting to see the idea that this is all kind of relative, right? There's no absolutes when it comes to polarity. Ketones are polar. Alcohols are polar. But probably, given the similar size molecule, the alcohol is going to be more polar because of hydrogen bonding. What functional group is this? That's a carboxylic acid. What can you say about its polarity? Even more polar, right? Because now you have the OH group, and you have 2 carbon groups pulling on this central carbon, so this is even more polar. Aromatic compounds are somewhat polar, and then amines, which are over here, are relatively polar as well. So polarity is relative, and polarity is one way that we separate things. So let's look at how exactly this works for this specific example. So what we're going to do in lab this week is something called column chromatography. All right, and column chromatography is used all the time by synthetic organic chemists. Now, I think I said this before, but separation is essential in chemistry. because we very often get byproducts that we don't want, and we very often use materials like sulfuric acid, which is used to make aspirin, that we don't want in our final product. So what we need to be able to do is get rid of the sulfuric acid, purify our aspirin so that somebody can eat it and feel better. Okay? So separation is absolutely essential. And again, we use distillation to do separation, but what we want to look at next is how we're going to do column chromatography. So when it comes to column chromatography, there's basically two things that we need to be aware of. Okay? The two things that we need to be aware of are the thing called the stationary phase, which is, in our case, silica gel. That's the powder that is stationary within the column. And then the mobile phase, which in our case is going to be toluene with increasing amounts of ethyl acetate, which is going to flow through and literally drip out of the column. So that's basically what we're going to do. So the molecules of interest, in our case, 4-nitroaniline and 2-nitroaniline, which are isomers, right? In one case, you have the nitro group in the 2 position here, and in one case, you have the nitro group in the 4 position here, the amine group in the up at the top, the amine group up at the top in both cases. But these are isomers, same number of carbons, hydrogens, nitrogens, and oxygens, but they have different polarity. And the two things that they're going to interact with, again, are the stationary silica gel and the solvent that is flowing through this. So in order to understand what's going to happen, we need to think about the polarity of silica gel and toluene with increasing amounts of ethyl acetate. So let's think about this a little bit first. Silica gel is essentially sand, okay? And silica gel is polar or nonpolar? It's actually very polar because it has silicon-oxygen bonds and oxygen-hydrogen bonds. So it actually has OH bonds that are very, very polar. Okay, now let's look at toluene. Toluene is methylbenzene, all right, where this is a CH3. What do you think about the relative polarity of methylbenzene? Only contains carbon and hydrogen. Relatively nonpolar. Okay, so this is relatively nonpolar. And we're going to add increasing amounts of ethyl acetate. Ethyl acetate is an ester. So acetate is that, and then ethyl is that. What do we think about the polarity of ethyl acetate as compared to toluene? It's actually more polar. Why is it more polar than toluene? It has oxygen. The oxygen is more electronegative. It can pull electron density away from this carbon, for example. So this is more polar. So, relative to silica gel, both of these things are not very polar. Ethyl acetate will not mix with water. So it's nonpolar enough that it's immiscible with water. However, it's more polar than toluene. Okay? So, what do we have going on here? We have a stationary phase. The stationary phase is very aptly named. It doesn't move, right? It just sits in the column. And then we have a mobile phase which flows over it. Our mobile phase is relatively nonpolar, and our stationary phase is very polar. So if our analyte, okay, in this case the 2 and the 4-nitroaniline, are polar, are they going to move through the column quickly, or are they going to move through the column slowly if they're polar? Slowly. Why are they going to move through the column slowly if they're polar? What are they going to stick to? They're going to stick to the silica gel. So if you have a polar analyte, it's going to stick to the silica gel, and it's not going to move through the column very quickly. If you have a nonpolar analyte, it's going to have no business sticking to the silica gel, and it's going to flow through almost at the same rate that the solvent flows through. Okay, there's some dead volume, right? It's not going to come out instantly because even the solvent doesn't come out instantly. It takes some time. But you're basically, this is what you've got going on. So the question that we have to ask ourselves is, Which of these two molecules are more polar? Now, the other thing that I need to tell you that's super important is, there's a couple of things. One, you want this to drip relatively slowly. Okay? If you just let this flow out as fast as possible, you're not going to separate anything. So make sure that this is dripping relatively slowly as you're going through this process. And we'll talk more about that in a few minutes. The second thing is, we have chosen for you a student-friendly version of column chromatography. What physical property about 2 and 4 nitroaniline makes this extremely student-friendly? Anybody know? What color are they? They're bright yellow. So you can actually see the separation occur. Normally, organic compounds are white. And if they're white, when they dissolve in solution, it's clear, and you can't tell if the separation has occurred. But we purposely chose bright yellow compounds for you. I didn't make this up. Somebody purposely chose bright yellow compounds for you so that you can actually see the separation occur. All right? So let's now talk about the relative polarity of 2 and 4 nitroaniline. Now, if you see here, we have what are called the charge-separated resonance forms. So essentially, this lone pair comes down here into a double bond. This goes here. This goes over here. And this goes out onto oxygen into a negative charge. So the electrons have flowed through this into a resonance form. Remember, resonance is a different arrangement of electrons. So we have the 2 charge-separated resonance forms. I'm going to try to point on the screen so people at home can follow along. So this is a charge-separated resonance form, and this is a charge-separated resonance form. Which of these 2 molecules do you think is more polar, and why? They're both polar, right? You both have charges on them. They both have heteroatoms. But which is more polar? This one is more polar. This one is less polar. Okay? And if we look at this, they both have an amine group and they both have a nitro group. So the difference isn't in the electronegativity of the atoms, right? It's the same atoms, so the same electronegativity. The difference is literally the difference in space. Here, the polar groups are further apart, okay? And here, they're closer together. There's lots of ways to think about this, but one way of thinking about it is this group can kind of help stabilize this group. All right, you have a positive and a negative charge relatively close together. Here you have a positive and a negative charge relatively far apart. Or you could just think about that the polar groups are further apart here and closer together here. That makes 4 nitroaniline overall more polar than the less polar 2 nitroaniline. So remember what we said before. Polar compounds are going to go through faster or slower through the column? Slower, because they're going to stick to the polar silica gel. So if you had to guess which of these 2 compounds is going to come out first? 2 nitroaniline. So this should come out first, and this should come out second. Okay, that's what we should expect to see. Now, we do not live in an ideal world where these things will come out instantly. So you're going to collect 4 fractions. 2 of the 4 fractions are going to have 2 and 4 nitroaniline in them, and 2 of the 4 fractions are just going to contain solvent because these things don't come out instantly. Okay, you're going to have to flow some solvent through there and collect that in a beaker, okay, in order to make this work. How will you know when to switch fractions? What will you see at the very bottom of your column when it's time to switch from, say, fraction 1 to fraction 2? The yellow stuff. So when the yellow stuff is about to come out, start collecting your next fraction. It's a huge advantage that this is yellow. Normally you would collect fractions by volume. So you collect 10 milliliters, 10 milliliters, 10 milliliters, and then you have to actually test to see which one has which thing, and then you can finally figure out, which fractions you can combine because they're essentially the same. So that's basically what we have going on. So let's take a look at how this is going to work. So we're going to start by adding our nonpolar toluene. Only nonpolar toluene when we start off. And what happens is, if you look at these kind of grayed circular ones, these are the solute or the analyte, and these are the solvent. And what's happening is the mobile phase is flowing through. And if the solute is polar, or if the analyte is polar, like 4-nitroaniline, it's going to be stuck to this OH group, so the silica gel, a lot. So if you look here, most of the molecules are stuck to the polar silica gel, and few are in the solvent. So if it's stuck a lot, it's not flowing through the column very quickly. It's staying at the very top of the column. That's what a polar analyte does. If you have a nonpolar analyte, the nonpolar analyte is going to be much less likely to interact with the silica gel, and therefore relatively more, in this case 4 dots versus 1 dot, is going to be in the mobile phase flowing through the column. If the analytes are in the mobile phase, they're moving because the solvent is flowing through the column, and therefore they're not stuck to the silica gel. So again, polar analytes go through slowly, and nonpolar analytes go through much more quickly. And that's basically what this is trying to tell us. All right? So that's basically that. As we run the column, what's going to happen is we're going to start to see some separation. Now in this case, when you first start the column, you have to put all of the analytes on the top of the column at the same time. In order to accomplish this goal, you need to flow the system so there's not very much toluene here. If, for example, you add your analytes when you have this much toluene at the top of the column, what's going to happen is that sample is going to dissolve evenly into this toluene. Then some of the molecules are going to hit the silica gel pretty much right away, and other molecules are going to be way up here, and they aren't going to hit the silica gel until 5 or 10 milliliters of solvent has flowed into the column. So it's really important when you load the column, you have the toluene down here. This is bad. You don't want to have it way up here, you want to have it way down here. And this is a very practical reason. If you have the solvent leveled way down here, then all of your molecules hit the silica gel at the same time. Having all of your molecules hit the silica gel at the same time will increase the separation. Okay? Then what's going to happen? We're slowly going to flow some toluene through the system. More toluene, more toluene. And eventually what we should start to see is, we should start to see a separation of these bands. Now, this picture depicts a very, very perfect case, okay, where you have very, very narrow bands. It's not going to be uncommon for your bands to be, this thick, an inch or two thick. So you're not going to see them be this real discrete band. They're going to be far thicker than is depicted here. However, what you're looking for is some clear space in between them. So yellow, and this is a better example, yellow, clear, yellow, you've separated the compounds. Okay, once you've separated them, it's pretty much impossible to unseparate them. So this is what you're going to do as you slowly allow this column to drip through. Now, when you're collecting fractions, in this case, pictures, this picture through this picture, should all be which fraction? Fraction 1. All of these should be fraction 1. So practically speaking, when do you want to stop collecting fraction 1? We already mentioned this before. When the yellow gets to the bottom. Before this yellow gets to the bottom, you're still collecting fraction 1. Should fraction 1 have any 2 or 4 nitroaniline in it? No. Did you do something wrong if it doesn't have anything in it? No, you actually did it right. So one common confusion is people want to have something in all their fractions. It's actually wrong to have something in all your fractions. You want to have nothing. Well, you have toluene, but you don't want to have anything but solvent in your first fraction. Okay? In this case, when A comes out, all right, this, and this picture alone, should be fraction 2. And what should be in fraction 2? This should be 2 nitroaniline. right? So, in this case, what color should fraction 2 be? Yellow. What color should fraction 1 be? Clear. Okay, so you collect fraction 1 until the sample reaches the bottom of the column. Then when you see that, you stop it, you get another container, and you collect fraction 2 until all of that yellow comes out. Note that there still be other yellow, B in this case, in the column. So you don't want all that to come out, you just want the A yellow to come out. And by that point, you should see clear solvent between these. Again, these bands are going to be much thicker than they're depicted on this picture. Fraction 3, we're going to then allow the solvent to come out, okay, until B, or in our case 4-nitroaniline, reaches the bottom of the column. But there's something else we're going to do in this area. And what we're going to do in this area as well is do what to the solvent? Yeah. So we're going to start with 30% ethyl acetate and then increase to 50%, I believe, ethyl acetate. Okay? We're going to use increasing amounts of ethyl acetate. Ethyl acetate is more polar. So what is ethyl acetate going to do? It's going to let 4-nitroaniline flow out. You could get 4-nitroaniline to flow out with toluene, but it might take you 2 or 3 liters of toluene to make that happen. So instead of using 2 or 3 liters of toluene, what we do is we increase the amount of more polar solvent, which then allows the 4-nitroaniline to have more affinity for the mobile phase because the mobile phase is more polar. And that's basically what we're going to do. The other thing is we don't just add straight ethyl acetate. Does anybody know what happens if we add straight ethyl acetate? The glass won't break, but the column will crack. And what it means by the column will crack is it means you'll see some clear liquid between, you'll have some silica gel, clear liquid, like I can't really depict it, and then more silica gel. Okay? So the silica gel separates from each other. And the reason that happens is there's a very big difference, not a very big, but there's a significant difference in density between ethyl acetate and toluene, so it can lead to cracking. So instead, we add a little bit of ethyl acetate at a time, and we avoid cracking. Finally, using ethyl acetate, we can get B to come out in fraction 4. And fraction 4 should contain our 4-nitroaniline. And fraction 4 should again be what color? Yellow. So essentially, fraction 1 is clear, fraction 2 is yellow, fraction 3 is clear, and fraction 4 is yellow. So 2 of our fractions should not have any analyte in them. All right, even though it seems like they should all have analyte in them, I hope now you understand why that's the case. So that's basically what we're doing here. Now, this is essentially where you stop for this week's lab. However, what are you going to do the following week to analyze these fractions? Thin layer chromatography. Okay? So we're going to do thin layer chromatography. So what I'm going to do is, I'm going to talk briefly right now, because it's the same idea, just upside down, about thin layer chromatography, and then next week what I'm going to do at this session, it'll be same time, same place, 1 week later, okay, is I'm going to go over the practice quiz. So that gives us time to go over the practice quiz. All right, and again, I'm going to try to record the video, so I'll put it on YouTube if you can't make it. All right, so we're going to do thin layer chromatography. How does thin layer chromatography work? Well, thin layer chromatography uses what's called a TLC plate. And a TLC plate is that same silica gel, it's finer particles, but it's the same idea, silica gel, adhered to a plate. Okay? And then you're going to spot your samples on the plate. Note that if you're spotting fraction 2 or fraction 4, which should be yellow, put enough spots so you can physically see yellow on the TLC plate. If you put one spot and you don't see any yellow on the TLC plate, put another spot. If you still don't see yellow, put another spot. You can spot it as many times as you want. Just let it dry in between. And it dries pretty quickly because it's just a drop. Okay? So you're just going to just put another drop and another drop until you can see yellow. Well, what's going to happen here? You're going to take this TLC plate and you're going to spot your samples, and we'll talk in a minute about exactly how we're going to do that. You're then going to dip that entire TLC plate in a covered beaker like this, and this just helps saturate the air with solvent so it doesn't evaporate as quickly. And what's going to happen to the liquid at the bottom of the beaker with respect to the TLC plate? It climbs up due to capillary action. So the liquid will slowly climb up the TLC plate. This is the same as if you put a piece of paper in water. The water will slowly climb up the piece of paper, even though the whole paper is not submerged, the whole paper will eventually get wet. So the liquid slowly climbs up. Now, our solvent here is going to be toluene. Our TLC plate has polar silica gel on it. So if you had to guess, which is going to travel further, 2-nitroaniline or 4-nitroaniline? The 2-nitroaniline should travel further. Why? It has less affinity for the silica gel. It's still polar silica gel. It's still the stationary phase. So the 4-nitroaniline should stick to the silica gel and not travel very far. And the 2-nitroaniline should travel further. So what I want to do is, I want to go over basically what you're going to spot. So the first thing you're going to have is a mixture. And 2 and 4. Okay? So you're going to have a mixture of 2,4-nitroaniline, you're going to have 2-nitroaniline, and you're going to have 4-nitroaniline. And you don't necessarily have to have them in this order. For the mixture, what do I expect to see? What's that?
You wouldn't see it.
Well, after I develop it.
Oh.
What do I expect to see for the mixture? Two spots. Okay? We should see 2 spots. Why? Because it has both 2 and 4-nitroaniline. So the mixture should see 2 spots. I am not saying this is where you're going to see the spots. I'm making this up. But it just gives you a general idea of what it's supposed to look like. Now, for the 2-nitroaniline, how many spots should I see? If it's pure 2-nitroaniline. 1 spot. Okay? So, there should be 1 spot. The question, $1,000,000 question is, where should that spot be? Right there. Okay? The 2-nitroaniline spot should line up exactly with the further spot on the mixture. Why? Because 2-nitroaniline is less polar, and therefore it's going to be pulled along more by the solvent, or it's going to stick to the silica gel less, which is usually how I think about it. This isn't going to stick to the silica gel as far, so it's going to go further. What should I see for the 4-nitroaniline? 1 spot right at the bottom, just like that. All right? Now, we're going to have TLC plates for our actual fractions. So, these are going to be our fractions. And they're going to be 1, 2, 3, and 4. So, fraction 1, what color is it again? Clear. Okay, what should I see on my TLC? You're going to see nothing. Because the first fraction has nothing in it. Alright, so you should see no spot. It is normal to see no spot because that first fraction is just what?
Solvent.
Just solvent. It's just toluene. The toluene is the mobile phase. You're not going to see that because you're going to evaporate that before you do it. For the second fraction, what color is it again? Yellow. What should I see? I should see one spot. And where should I see that spot? The higher spot or the lower spot? The higher spot. So I should see one spot right up there, because that's 2-nitroaniline. Remember, spot the TLC plate until it turns yellow. Okay? Make sure you spot it enough times so you can actually see the yellow. So spot, blow it dry, spot again, blow it dry. You can just blow on it. All right? And it'll dry faster. Fraction 3, what should I see? Nothing, because it's just solvent. And fraction 4, I think you get the idea. I should see a lower spot for the 4-nitroaniline. This is what you're going to interpret when you write your conclusion. So when you're writing your conclusion for the lab, look at your TLC results, and you could say, I proved that in fraction 2, I have 2-nitroaniline because it has the same spot as the standard 2-nitroaniline over here. Okay? Mathematically, what do we calculate for the spots? So we have a number to associate with what I just said. The RF, okay, which is the retention factor. And all this is the distance that the sample moved from the center of the spot divided by the distance that the solvent front moved. So make sure when you take your TLC plate out of the liquid, you just put a line on it where it's wet, at the top of where it's wet, so you know how far the solvent moved, and you just take a ratio of those things. The RF definitionally must be between what two numbers? 0 and 1, right? If it goes exactly the same distance as the solvent front, it'll be 1. If it doesn't move at all, it'll be 0. So the RF has to be between 0 and 1. It's a fraction, essentially. Okay? So that's basically how we want to do that and calculate the RF. All right. So this is for the other class. Let me get a blank sheet of paper. So one thing that I know everybody wants is a separation scheme. All right. So we have 2-nitroaniline and 4-nitroaniline. And we're going to do column chromatography. All right. What should I put for my location over here of 2-nitroaniline? Fraction 2. And over here, fraction 4. Okay. A couple other things. You are required to look up the physical properties of these molecules for the beginning of your lab report. I believe you need the molar mass, the melting point or the boiling point, and the density. Okay. Where can you find those? Online. Wikipedia. All right. Other places do, but Wikipedia has them. I checked this morning. Okay. The separation scheme is required when you hand in the lab, but there's not much to it. You can just do it now. Okay? All right. So let's just wrap up by talking about a little bit of what you could use in your hypothesis. Okay? First thing in your hypothesis is which fraction should you find these things? Okay? And we've pretty clearly laid that out in several cases. But fraction 2 should contain our 2-nitroaniline, and it'll be yellow. Fraction 4 should contain our 4-nitroaniline. Next thing I want to talk about is how does column chromatography actually separate things? It separates things based on their polarity. More polar molecules will have a stronger affinity for the stationary phase, which is polar silica gel. All right? Therefore, they will move through the column less quickly. Less polar things will have a weaker affinity for the polar silica gel, and therefore they'll move through the column more quickly. By doing it in this way, we can separate the two molecules and have our 2-nitroaniline in fraction 2 and our 4-nitroaniline in fraction 4. The last thing I want to remind you is the quizzes in this course are about theory, okay? You're not going to get questions like, how many milliliters of toluene did you pour into the beaker in order to do your TLC? Okay? If you want to know how many milliliters to pour in the beaker, I don't know off the top of my head. Okay? I'd have to look in the lab manual to find out. They're going to be more like, if you did column chromatography of these two molecules, which would come out first? And one might be a ketone, and one might be an alkane. Okay? And so if I had an alkane and a ketone, which one would come out of silica gel column chromatography first? The alkane, because alkanes are less polar than ketones. Ketones are more polar, and it goes back to what we were talking about at the beginning. So column chromatography is a way to separate molecules based on their relative polarity. So I hope you found this a little bit useful, okay? And if anybody has any questions, I'm going to turn this thing off, but I'd be happy to answer any questions that you have as well. I'm going to try to turn this off. All right. Anybody have any questions? All right.
So the quiz, is it going to be before or after the lab?